Stuckey, and I'm going to talk to you about why there are no integers, or why there can be no integers in discrete optimization models, which I hope is a little bit surprising because integers make up the bulk of discrete optimization models. This is joint work with Decker and Gitattack. So a warning of what's coming ahead. When I was invited to do this talk in December, of course we just had this idea and it seemed very exciting and we were going to pursue it, and of course it would be done by now. But as is the nature in programming language research, things always take longer than expected, and so I'll be talking about some decisions we've made which are only partially implemented and certainly not available in any releases of MiniZinc so far. So vaporware ahead, I'll try to make it explicit where that's happening. All right, let's talk about modeling languages. So that's what we're going to be dealing with. So these are languages designed to express, in our case, discrete optimization problems, and they translate them to a form suitable for solvers. So there are a small class of domain-specific languages, and examples out there from the mathematical programming kind of background are AMPL, GAMS, and AIMS, and from the constraint programming background there's OPL, MiniZinc, and Essence, and I'm going to talk about MiniZinc, which is our modeling language. All right, what's MiniZinc? It's a modeling language for discrete optimization problems. It's solver independent, so it'll map down to various different solvers. It's high level, it's extensible, and it's pretty widely used around the world by various optimization people to build their models and run them. So the key thing is that the modeling language doesn't do any of the hard work. So it's this underlying solver that does this, and one of MiniZinc's strengths is it supports lots of different kinds of solvers: constraint programming, SAT modulo theories, mixed integer programming, SAT, and local search solvers. And we've got to remember that when solvers are given a problem, they typically have a very restricted format. So they can take a set of decision variables, and that might be just one type. If it's a SAT solver, it's only going to be Booleans, and a conjunction of constraints. And again, that's often quite restricted. If it's a MIP solver, it's probably only going to be linear constraints. And so what MiniZinc does is it takes your model and some data, maybe some library definitions of global constraints you're using in the model, and it translates that into what's called a FlatZinc file, which is what's actually sent to the solver. And then the solver does the hard work and then outputs a solution to your problem. So, global constraints are one of the key features of constraint programming modeling languages, and one of the differences with the other ones, although things like AMPL are beginning to introduce global constraints. And what they do is capture a frequent combinatorial structure. So that's good because they make models more concise and more high level. They also allow specialized encodings of those constraints to be used in different solvers, different encodings in different solvers. So it typically makes them faster to solve. And examples are like all different table, regular, cumulative, bin packing. There's over 200 in the global constraint catalog. It won't really matter how they work. We'll show you one or two examples of global constraints. Just it's important for you to know that they are a feature of both the solving and the modeling language. All right, so let's have a look at a MiniZinc example. So this is a model to choose k products from a set of n products that you're given within some weight limit to maximize the profit. And so if we look at the first couple of lines, this is all parameter information. So k is the number of products we're going to choose, limit is the available weight limit, n is the number of products that we have, and we're just setting up a name for the set 1 to n. And then for each product we have a weight and a profit. So that's the data, the parameters. And then the key thing that the solver has to do is work out the decisions. So here we're saying we're going to pick k different products. So they're variable products. That's where we're telling it's the solver's idea to fill in the values for this chosen array. Now we can't pick a product twice, so we're using a global constraint here, all different, to make sure that in that array everything is a different product. And then we've got a constraint here to check the limit. So we sum over the 1 to k of the weights of the chosen items and check that that's less than or equal to the limit. And notice here we've got this variable lookup. So chosen of I is a decision variable, so it isn't known at compile time, where MiniZinc's processing this model. It'll be known when the solver makes those decisions. It'll be able to look up the weight. It's one of the most powerful modeling facilities in constraint programming languages, and one of the reasons that actually a lot of MIP modelers use MiniZinc. All right, and then we maximize the profit. Okay, so there's my working model. It gives me answers, all's good. All right, so let's talk a bit about debugging optimization. So unfortunately, once the model compiles, that's when the real problems begin. So there can be lots of reasons that your model is wrong. there could be too many solutions. This is actually the easy case, because usually you have the smoking gun, you have the wrong solution in front of you, and basically you can use that to test your model and say, well, this is meant to be removed by one of the constraints in my model, so that obviously that constraint is wrong, so I can fix it up. So that's the easiest kind of bug. You can get too few solutions. So your model just might say unsatisfiable, saying there's no solution to your problem. Now, if that's the case, we sort of try to look for a minimal unsatisfiable subset of the constraints, so a set of constraints which make sure that this has no solution, and we can sort of turn them off and on and eventually explore which of them is wrong. One of them in the minimal unsatisfiable subset must be wrong, and we can track down what's going wrong. But we can do worse than that, and that is we can just run our solver and get no answer, right? Basically, the model never returns. So it just keeps running. And we don't know, is this a bug? Is this because the model is wrong? Or is it just that the problem we're asking is too hard? Because we're solving NP hard problems here, the times to solve them may be just longer than we're prepared to wait. So debugging optimization is not so easy, right? There's no really notion of trace debugging. So solvers can be black boxes. They might be a commercial thing where they definitely don't want to let you look inside them. And even if they do look inside them, if they're open source solver, the search tree, so any kind of discrete optimization is going to do some kind of search. It's going to have millions of nodes, and it's not at all easy to work out what's going on by looking at these kind of things. So the key takeaway I want you to take from this message is that if we have the compiler recognize errors in our model, that's extremely valuable, because debugging optimization models is really hard. We want to avoid as much of that as we can. So let's talk about the types for MiniZinc. So this is the original MiniZinc type system. It's very simple, and it sort of reflected solver capabilities. So we have Booleans, integers, and floats as the base types. Sets of integers, which can be decisions. We have sets of floats, but they're not decisions. They just have to be fixed. They can be useful for specifying data. And then multi-dimensional arrays of the above. And so no arrays of arrays, just multi-dimensional arrays. And automatic coercion, that Booleans coerce to integers, coerce to floats. And that's basically it. And you can see actually it's more or less, it's apart from the not limit on the dimensions of the arrays, it's basically a finite type system. All right, let's talk about integers. So integers are ubiquitous in discrete optimization problems. They're used to model sets of objects. We give them names like we did in the example there, 1 to n. They're used to model things like position if we're doing a packing problem. Where does something go in the truck? They're used to model time if we're doing a scheduling problem. When does something happen? And they're also used to model order. So the thesis of this talk is, how can we remove integers altogether from a discrete optimization modeling language? So obviously I'm going to cheat, but hopefully you'll go along with me. All right, let's look at removing integers and enumerated types. So enumerated types are in almost every programming and modeling language. And this is very useful because many optimization models reason about sets of objects. So inside the solver, clearly these will be represented by integers, but in the model we're much better off using an explicit type which talks about the objects that we're reasoning about. And that's the role of enumerated types. All right, so enumerated types, just like in almost all languages, are basically a named set of entities. You can also have an anonymous set where you're just saying the size of it, but you don't care about the individual names. You can't actually talk about the individual names in an anonymous enumerated type. And see, these are very standard in almost every programming language. There's some form of enumeration, even if it's just done by erasure and doesn't really actually help in type checking. So enumerated types are great because they help you document your model better, and they're very important for type safety of models. So let's go back and look at our model that we were doing before. Why would we want to use enumerated types? This model seemed fine, it already worked. Obviously the products is an enumerated type. So we can basically replace that saying the number of the products and just have an enumerated type product, which will give us the set of products available and map each of those products to the weight and the profit. And the interesting thing is, with this small change, suddenly this model fails to compile. So what was going on? Well, actually, in the last line, if you look at it, we're summing up from I1 to k the profit of I, but profit is a mapping from products to integers, not from integers, right? So there's actually a type error here, which, because we were using integers for everything, we didn't notice before. And so now, immediately, by moving towards enumerator types, we've got some better detection that there was actually an error in here. I shouldn't have written this sum I1 to k of profit of I. It should be profit of chosen of I, just like it is in the line above. So, enumerator types are very valuable for detecting type errors. So, enumerator types in MiniZinc are ordered, and they support operations like equality, disequality, comparison less than or equal to, enum next and enum prev to get the next and previous element in the enumeration, and you can take min and max of sets of enumerator types. And we have explicit coercion from integers. If you really want to break things, you can build the ith element of the enumerator type person by this call to enum person of I. And currently, they automatically coerce to integers when you apply an arithmetic operation to them. So in fact, we can kind of think of enum next, the function, to be implemented as this way. Basically, it takes an enumerated object x. When it does x plus 1, it basically coerces that x to an integer, adds 1 to it, and then we're using toEnum to coerce it back to the enumerator type $$t. And this is wrong, of course, because actually we need to check that x is not the maximum of that type, because then enum next is undefined. And undefinedness and modeling languages have a very complex relationship. We shall try to avoid talking about that much, but I will have to talk about it later on, where we'll talk about default behaviors in order to try to avoid having difficulty avoiding undefinedness. All right, and now on the side, and here's my first vaporware disclosure: unordered enumerations. So many sets of objects have no natural order. So for example, the products in our example here, then there's no notion that why they should be ordered. And you can clearly build an unordered enumerator type which only supports equality and disequality. But there's some problems arise that make this difficult. That's why we haven't implemented it so far in MiniZinc. Is that you often want to iterate over pairs. So we want to iterate over pairs of products, let's say, or objects. And the usual way is you iterate over x1, x2 in this set, and then you constrain that x1 is less than x2, and of course then you're using the order between them. And this is a way of getting just every pair rather than like getting every pair twice. I could write x1, x2 in object where x1 is not equal to x2, but then I look at every pair twice. So we can either do something like an alternate syntax, which you can see there, where we can enumerate subsets of size 2. That would fix the problem, but often we also we might want to be adding ordering constraints to do symmetry breaking. So almost certainly we will be adding unordered enumerate types to MiniZinc, and there's some definite advantages. Because it prevents comparison of elements, it stops you doing things which you shouldn't do with these unordered types. And it also allows for automatic symmetry breaking detection, because if you can look at this type and you can see that you never look at individuals, then you know that the elements are all essentially symmetric with each other, and you can add automatic symmetry breaking constraints to improve your model. Of course, when you add these symmetry breaking constraints, they actually add ordering they make use of the implicit ordering amongst the elements, and so that breaks the abstraction. But if this is done sort of below the level that the modeler can write and just in the system level, then that's fine, because let's be fair, in the end, these are all integers anyway. All right, so let's look at removing more integers with type extension. So sometimes we use integers, but we really like to use a numerator type. So here's a fragment of a MiniZinc model, which is about buying pizzas. So you've got a whole lot of pizzas that you want to buy, and you have some vouchers, and the vouchers basically say buy 2 get 1 free, or buy 3 get 2 free, or whatever. And basically we want to work out how to buy the pizzas as cheaply as possible. And one of the key decisions when I'm doing this model is I want to say for each pizza, how do I purchase it? So I can purchase it in 3 different ways. I can purchase it for free with some voucher j, right? So here I'm using how minus j to say I got this pizza for free using voucher j. I can just buy it, not using any vouchers, and then I say the how of how I bought it is 0. Or I can buy it in order to enable a voucher. Right, so if I use plus j, then I'm buying this pizza in order to enable the voucher. So maybe I have to buy 2 of these things with plus 1 using voucher 1 to enable me to get one thing with minus 1 for free from voucher 1. And a key constraint in this model is saying, well, if we look at every pair of pizzas, if one was used to buy the voucher, and another was used to get for free for the voucher, and obviously it's P1 that's used to buy because it's positive, then the price of P1 should be greater than or equal to the price of P2, right? So this is the thing with vouchers, buy two, get one free, is that the two that you buy have to be more expensive than the one you get for free. All right, so there's a little bit of a model, and we're using these integers minus m to m to sort of encode the decision, how we did something. So how do we do that? Well, we can't do that directly with enumerator types as defined so far, but we can once we add type extension. So type extension is basically discriminator union type, but only flat discriminator union types. So we can replace our vouchers with an anonymous enumerator type, and then we're building this use type in order to replace that, right? So vouchers we don't use integers, we'll use an anonymous enumerator type, and then we'll build a new type of uses, which is making use of these type constructors f and b, right? So f of a voucher means we get this piece for free using some voucher. None means we just buy it, and b of voucher means we bought this pizza in order to enable a voucher. And once we do this, right, we got rid of all the integers here, except the number of vouchers at the beginning. And indeed, it also arguably makes it easier to understand the expression of this constraint down below. Because if I look at this, it says, okay, if b to the minus 1, so this is the voucher I used P1 to help purchase, and if I use that same voucher to get P2 for free, it should be that P1's price is greater than or equal to P2. And here we're making use of the fact that this inverse function, b to the minus 1, is partial, right? So if the usage of how P1 is not b of something, then this will just fail, and then that constraint will be false. So we can write, the relationship between the buying and the free pizzas for the same voucher is a bit more straightforward. All right, so type extension, basically when we do this definition, it adds these constructor functions f and b, which are essentially mappings from voucher to use, and we automatically construct these partial deconstruction functions, f to the minus 1 and b to the minus 1, which map the other way, and of course return undefined if we're trying to map the wrong kind of usage. And we add new constants to the type none. So here the none happens in the middle. And the nice thing about this is once we've done this, our programs are more type safe, they're more concise, and they're more self-documenting, we would ask. And it's actually quite straightforward to implement these things basically as a source-to-source transformation. So basically we can create a new anonymous enumerator type use just by counting the size of the elements, and we can create these functions f and b and constants, etc. Just in MiniZinc itself. Here, making use of the fact that when we start to do arithmetic on a enumerator type, then it automatically coerces to an integer. All right. And let's go on. Once we have these complex subtypes, which occur very frequently actually in discrete optimization models, then we're going to end up generating quite complex expressions. So here's an example, a very powerful example of a part of a discrete optimization problem, which is vehicle routing. Okay, so we have trucks, we have customers, we have locations. For every customer, we have a location, and we have a travel time between pairs of locations. And the depot is a location where the trucks start. And the way we model this is a sort of grand tour example where we have one node for every customer, a start node for every truck, and an end node for every truck. So they just record basically when does the truck leave the depot and when does the truck arrive at the depot. And the decisions we have to make are basically when does things arrive at each node and the next node. So we basically build up a huge circle by connecting the end of one truck to the start of the next truck. We end up with a big cycle, and this allows us to write the very efficient model. So when we're doing this, of course, one of the key things we have to do is ensure that the arrival times respect the travel time. And this is what we do here is we look through all the nodes which are not end nodes, because end nodes don't have any next node that is meaningfully attached in terms of time. And we say the time that you arrive at the next node is got to be greater than or equal to when you were at the previous node plus the travel time between them. And to work out the travel time, basically, remember travel time is mapping location and location to distance or time. we have to check if it's a customer node, then we just look up the location of the customer. Otherwise, it's the depot. The truck and the start and the end locations for the truck are always the depot. And we do that for both the first argument and the second argument. You can see we get quite complicated expressions like this one. So it turns out that this is quite common once we start using type extension. So we introduce the x default y to MiniZinc, which evaluates to x if it's defined and y otherwise. So it's a way of capturing undefinedness. And notice we have to be able to do that for our models anyway. Once we do that, we can rewrite these things much simpler. So we just do this inverse left lookup of a node. If this is not a customer node, this will return undefined. And then if we look up an array at an undefined location, it's of course also undefined. So this whole thing will be undefined, and we'll just get the depot, which is of course what we want. And so this works for both of those cases. So this is a much more succinct way of writing the same expression, just making use of this default behavior. So if you want, it's a sort of simple case expression, worried about definiteness or undefinedness. And one of the good things about this is we can actually compile away expressions of these form. So the user writes that expression as we saw on the previous page, but what actually happens inside the model is we're going to build an extended version of the location array, which basically has maps. So we had location array mapped customers to location. What we really want to do is map nodes to location. So we can build an extended version of the array which maps every node, if it's a customer node, to its location, and otherwise maps everything else to a depot. And once we do that, we can basically just replace all of this default behavior by just using this lookup in this extended array. And we can do this automatically within the compiler. And so that's a power of the interaction of extended types and default implementation. So once we have type extensions, it's worth having case statements. We know how to do it. We haven't yet done it. It's also interesting that we need open intervals where we don't include some of the endpoints. This is very useful for enumerated type iterations where you want to do everyone but the last. It's very clumsy to write that if you don't have these open intervals. But this is all just syntactic sugar, very straightforward. And the case expression is just waiting for us to actually do it. All right, so introducing enumerated types allows us to reason about name objects, build new sets of objects out of existing sets of objects. That's the key thing why we need type extension. And so we can reason about all the objects in our model in a type-safe way. So what's wrong with this model? So since it's a recorded talk, I can't ask the audience, so I'll give you a few minutes to sort of stare at it. You could basically, it's going to be somewhere where it changed, so it's going to be a bit of a giveaway. All right, so this model all sort of looks good. I've made sure that I look up weight, it's type correct and everything. But if we look at this sum here, we're summing up the profit of each of the chosen items, and we're comparing it to the limit. And the profit is about worth, and the limit is about weight. So there's something wrong in this constraint. Nothing type incorrect, but something wrong. So the other way we want to remove units is essentially by unit types. And as I said, this is vaporware. We have some partial implementations. We're still exploring things. So you're going to have to take this as a grain of salt. So with unit types, what do we want to do? Well, we can attach units to our integers, right? So essentially, we know that the limit is about kilograms. So that's the unit of these integers that we're talking about in the limit variable. The weights are about kilograms. The profits are about cents, right? Now, if we write this model, the compiler can detect an error. Essentially, it looks at this and says, well, you're summing up a whole lot of cents, that's fine, and then comparing it to a weight, and that's not fine. So the linear equation involves two incompatible units, and so we get a type error, and that's nice because I'd much rather have that type error happen before I run the model rather than staring at the output, not understanding why I'm getting results that don't make any sense to me because I have realized that I haven't written the right constraints. So unit types, there are a lot of versions of unit types out there, and the basics are all the same, right? You basically define dimensions, which are the types of the unit which are compatible. So we have a dimension in weight and a dimension in worth. And then you define units for each dimension. So one of the weight dimensions is grams, and then we can define kilograms in terms of grams, tons in terms of kilograms, US tons in terms of kilograms. We can use cents and dollars, and we can also use Unicode symbols in MiniZinc. So often that's a nice way of building a unit, because there often is a Unicode symbol for the unit. So if we go back to our model now, here's our correct model. So how do we put in the data, right? So here's some data for this model. So here we've got 3 products, A, B, and C, and we're going to say the limit is 1 ton. Okay, it's meant to be kilograms, but obviously 1 ton is compatible. It's also a weight unit, so that's fine. The weights here are given as kilograms, and the profits in cents and dollars. And one of the nice things about unit types is they allow this automatic scaling. So I can put down $2 here, and of course that's the same as 200 cents. I can put down 1 ton, that's the same as 1,000 kilograms. So that's one way of doing it, but actually most people don't want to deal their data with all this unit stuff in it. You can also, of course, just use integers and in your data, and then are going to inherit the unit which is defined in the declaration of the model. Right, so that's a much simpler way of writing the model. Both ways are possible. All right, and units get interesting when you derive one unit from the other, right? So once we define a distance type, then we can also derive an area type, which is distance times distance. If we have a time dimension as well, we can have velocity dimension, which is distance times time, and then we can build derived units from the existing units from those underlying dimensions. All right, so this is standard unit type stuff here, nothing very complicated. Although one thing I'll say is that in modeling languages, we don't actually do a lot of physics stuff. And so we don't have hugely complicated unit expressions being generated. And there's another interesting case is that many of our solvers really want integers. They do not want floating point numbers. And so many times we need our units to be integral in order to make solving easy. And you saw we still had this int attached to the unit type, right? Why didn't we just remove that altogether from the declaration? And that's because we may require it to be integer. And so you can see if I had this data file for our example, then there's going to be some problems, right? Because 1 US ton is, I can't remember what it is, 907.185 kilograms. It's not going to give me an integer number of kilograms for the limit. And limit is meant to be an integer. And similarly, 234,001 grams is not an integer number of kilograms, and weights are meant to be talking about integer numbers of kilograms. So currently in MiniZinc, this is an error. So basically we'll, when we detect this kind of behavior or the possibility of this behavior, because we may not actually have these numbers, then we're going to say, well, sorry, we can't guarantee it's integer and we're just going to stop the compilation. But in many cases, rounding up or down may be fine. It's not always clear which way to go, and there are certainly models where we use 2 different scales of the same dimensions. So for example, in scheduling, we'll often schedule tasks to the minute, but check resource usage to the half day or something like that. And so it's interesting, it's something we're still exploring if we can do some easy ways of controlling what we do with these kind of things which don't hit the integer. Is it, can we make it rounding up or rounding down? Is that going to be sensible for many models? Another more important thing, and this sort of comes back to the point I was talking about before, that we often use different units in the same model, even for the same dimension, is a discrete optimization model can be applicable to many different unit types. So we don't want to rewrite the model each time just because we're now dealing with, I don't know, a different kind of knapsack problem. So if we go to our knapsack problem, really there's 2 things going on in the knapsack problem. There's some limit dimension that we're going to limit, and there's some worth dimension. Right, so we can introduce basically an unspecified limit dimension, a new dimension, and we have limit units, and then some unspecified worth unit. We don't really care what worth unit we're calculating in. As long as all the profits are written in the same worth unit, it's fine. We can work out the maximum profit. So we don't care if it's dollars or cents or millions of dollars or whatever. None of that really matters from the optimization model perspective. So making use of these unspecified or new dimensions and unspecified units is very valuable. So we can use those in the declaration just as we did before. And they can be given in the data, right? So we can say that our value unit happens to be cents if you want, and then the profit will still work. We'll be able to read in those things. It knows what dollars means. The limits are in this unspecified value unit, so we're not going to put any VUs next to them. We could have VU next to all of them, but we can just avoid the VU and just read in the data as is using the weight unit, whatever it means, we don't care. So that's a less often in unit types example, but it does exist in other extensible unit type definitions. All right, here's another kind of unit type, which is we've seen sort of one or two examples of around the place, but it's much, much rarer and very, very useful in discrete optimization modeling. So unit types can expose a lot of errors, but you can still get a lot of subtle errors that can hide. So here's a disjunctive constraint. So this is a scheduling constraint, which is it's given an array of start times, an array of durations, and it says make sure that there's no overlap between the tasks where task I starts at S of I and has duration D of I. Right, so we've got to reorder the tasks so that they're all non-overlapping with each other. And the disjunctive constraint is ubiquitous in scheduling problems. But we can certainly write this constraint, disjunctive duration start, so we can flip the durations and the start times, and that's perfectly type correct, right? They're both unit of times, they're both time unit kind of things, so that's perfectly valid. No unit error there. So delta unit types differentiate between two things. There's those things which are an actual measurement with respect to some origin, right? So the start time is the measurement of a time with respect to some origin, typically in scheduling, the start of the scheduling problem. And delta types are the differences between two of these measurements, right? And once you have this difference between measurements and deltas, then this interacts with addition and subtraction. So you can take a time plus a delta time, you'll get a time back. You can also do delta time plus time because we want plus to be commutative still. If we take two delta times, we can add them together to get a delta time. And ideally, if we take two times and add them together, that should be an error, right? That's sort of the most powerful usage we could get out of delta types. But we're a bit hesitant to do that. I think we'll have modes where that will be enforced. But because if you think about in our example, we're adding up a whole lot of weights, but we don't want to think of them as delta weights. The only thing we do with the weights is add them up and divide them before the limit. And so forcing us to use delta types there would be bad. The option is if we never mention the delta type, then we allow t plus t, but if we do mention the delta type, we don't allow it. Currently, we are still allowing it regardless of whether delta types don't or do exist for that particular unit. And of course, t minus t, that gives you a delta type, t minus delta type gives you a t, and delta type minus t is an error, right? So delta types allow us to find more bugs in our model because we start getting the wrong thing, right? You should have one measurement and add some deltas to it to get a new measurement. And note that delta acts like a normal unit for multiplication. If you have a delta t, and you multiply that by some u divided by t type, you get a delta u. So we can look at a scheduling example and see how that plays out. Here's a job shop scheduling problem, and basically for every job, we make sure that the task finishes before the next task, right? You can see that that's take a time unit plus a delta time unit and comparing it to another time unit, which is type safe. And when we call the disjunctive constraint, we're taking an array of time units and an array of delta time units. And that's exactly the case that disjunctive is meant to work on. All right, let's keep removing integers. And even more vaporware here. As you'll see in the discussion, there's some things we don't know exactly how far we want to go. And I'll talk to that as we get to them. Right, if we looked at our knapsack problem, there was still one integer left. Right, there's this thing here, k. The number of products to choose. So what's the correct unit here? That's the question. So I think it's pretty obvious that what k is a counter of products, right? And indeed, what we really find in discrete optimization models is every enumerated unit type sort of really introduces its own unit type, which is for counting elements of that type, right? So indeed, the sort of correct type of the cardinality function, which takes a set of some type t, it returns an integer with the unit given by that type t, right? And indeed, discrete optimization problems frequently involve counting, right? We frequently have constraints which count how many times something happens, etc. So we can actually finally produce our knapsack problem without any integers at all, well, without any integers, without units, that is. Of course, the integers are still there, right? So k is an int which counts products. And in fact, we'll introduce a range type here, taking from one product to k. K obviously already has the unit. The product here, of course, we've seen before in the data files example, is if we take a unit number and append it onto a dimensionless integer, then we get the unit version of that integer, just in most, same as in most unit type definitions. Right, and with this, you can see there are essentially no integers which do not have an attached unit. All right, but there are more complicated cases. So sometimes we really want to have an enumerated type of different resources. So here is a production planning model, right? We have a set of products, we have a profit for each product, how much we get for each element that we build of that product. We have some resources, we have a capacity for each resource, and then we have a consumption for every product. How much does it use of each resource? And then our decisions are basically how many of each of the products to produce, and we can't produce negative numbers, obviously. And there's really one constraint which says if we sum up over all the products, the amount of resource we use for every possible resource, that has to be less than the capacity, and we want to maximize our profit. So how do we make this unit type safe? Well, the answer is each item in the enumerator type also defines a unit. All right, so if you think about this, every product also defines its own unit type for counting that particular product, right? Every resource defines its own unit type for counting that particular resource, the usage of it. And so we can now start to do things like this. We can use different units per element, right? So here we're saying the profit is actually the number of dollars per product for this particular product, right? And you can see we use this iterator in the definition to give essentially different units to different elements in the array. And we can build our counter type per product. Obviously, when we're producing P's, right, we're producing from between 0 P's and infinity P's for each product, right? So the produce array is also of type P for the Pth element in the array. And then we can check in our constraint here, it is in fact unit type safe, right? Consumption is resource per product, the particular resource for the particular product. We multiply that by the same particular product and we compare that with the same particular resource. So here we're counting the use of each resource and each product separately. And so we get type safety. We can see we're now getting quite complicated unit types where elements in an array have a different unit that is attached to the index of the array. So this index dependent unit types are quite complicated, and type checking for this example is easy enough. And if we look at the examples we typically see in discrete optimization models, it's also fairly straightforward, but there's a limit to how complex the unit types are that we can manage and effectively type. But so far we've seen that the syntax that we allow, basically where you can only have an iterator name in the definition of the array, it restricts the complexity of what you can do. And does it lead to more actual type safety? Maybe we could get away with the same thing with some kind of restricted parametric polymorphism, because there's almost some theorems for free things going on in this example, if you think about it. All right, last thing we'll talk about for removing integers is ordering. So often discrete optimization problems involve some kind of ordering or ranking of objects. And so here's an example. This is the old-fashioned stable marriage problem. So yes, the last and most complicated model, I'm afraid, I'm going to make you look at. So we have n men and n women. They're defined using anonymous enumerations. And then each woman ranks every man, right, from some number. So basically how much they prefer them, the lower number, the better. And similarly, each man ranks every woman. And then the decisions we're trying to do is pair off these people into n pairs, right? So the wife of the man is is a woman and the husband of the woman is a man. That's why I'm saying it's the old-fashioned stable marriage. We can do much better, much more nuanced versions nowadays. So if we look at the constraints, the first two, you actually only need one of them, but they both say the same thing. Basically, they say that the husband and the wife pairing agree, right? If W is the wife of M, then M is the husband of W. And then the critical point is this stable constraint, the stability constraint, which says if a man M prefers a woman O to their wife, then woman O has to prefer her husband to M. So otherwise, there's this instability that the man M and the woman O would prefer both to be together than their current partners, and they would leave, and therefore we get non-stable marriage decisions. And we have the same thing for the women as well. All right, so you can see we've used some numerator types here for the men and women, so there's no problem there, but we've got these rankings. So we can use a unit associated with a unit type to be a ranking, right? So we can introduce a ranking type here. So rm1 to n is just basically using type extension to map the numbers 1 to n to a ranking type, and because our enumerator types are ordered, we can compare these things, and that's exactly what we want to do. Right, and so here we can check, so for each woman, they actually make a decision which has got a unit of ranking men, right? How each woman ranks each man. And when we're looking at the men's rankings of the women, then the unit type of their integers is this ranking of women. And if we do that, then we're going to make sure that we can't compare male ranks with women ranks. Okay, there's no error in this model because the model's correct, but if we tried to write something like that, we'd immediately get a unit type error. So that's good. But actually, if you think about this problem, we actually only compare each man's ranking of the women or each woman's ranking of the men with their own ranking. Basically, we only decide between the same person what they do. So we can instead use this idea that every element in a numerator type also defines a unit. And so here we say the ranking for the women is basically this integer of that woman, the particular woman that we're looking at, the row that we're looking at. Her rankings are attached to a unit of the same as her, and similarly for the men. And when we do this, then we can't actually compare one male's rank with another male's rank. They'll be different unit types. And so that'll avoid some much more complicated errors. And we only actually ever compare, you can see, we look at rank of M, rank men of M, and rank men of M, rank woman of O, rank woman of O, right? We only ever compare ranks of the same person, right? So using that person as the unit type for that ranking is a way of making sure that's the only ones we can compare. So that's a way of making this much more type safe in the sense that there's many errors that I cannot do anymore without doing a unit type error. All right, so in conclusion, I hope I've showed you that we can remove all integers from a discrete optimization model, right? Basically, objects are represented by enumerator types. Parametric data can give the appropriate unit types if we want them to be part of the data. And this is going to improve type safety and hopefully also the comprehension of models. But hang on, what about this one? Stable marriage, we still have this one integer left here. Now, it's true that you can look at this and say, what is this integer n? It's actually a counter of people, both men and women. And you could think of some complex way of saying, well, we're going to build a men counting type, men counting and woman counting unit and just ensure that they're the same size. We'll jump through a lot of hoops in order to get rid of this integer n. So this really feels like a case where adding units to try and express this correctly without some sort of cyclic dependencies is going to be tricky, and it's not going to help our model at all. Right? So sometimes in discrete optimization models, there really are integers, which are just defining dimensionless sizes, or in this case, multi-dimension sizes, and it maybe not be worth adding units. Of course, you'll always be able to use integers without unit types in MiniZinc, but we'd like you to not do so. So, in conclusion, enumerator types and type extensions, they've all been implemented for a while. They're definitely worthwhile. We looked through the MiniZinc challenge models, which have been submitted over many years, and we found 15 of the 129 previous models could be improved with extended types, have better type safety, and 64 of the models could be improved just by using enumerator types, basic enumerator types, which also shows you that modelers are not yet taking advantage of enumerator types, which are been in the language for a long time and are very valuable for improving your model. And default expressions, as we showed, can be compiled by MiniZinc to extended arrays, and that's really quite valuable because it essentially does, the compiler is sort of automatically creating what an expert would model. An expert would model this directly because they know that this kind of constraint is very efficiently solved that way, and indeed you get a 25% improvement in solving efficiency essentially on these kind of examples that I showed you just by using this extended array approach, which is what an expert modeler would do. What about units? So we have experimental implementations of some of these things, and some of the things are straightforward. Simple units are valuable, they're easy, and it's interesting that in discrete optimization models, nonlinear constraints are quite rare, right? So the units are actually quite simple. We don't get this whole like meters per second squared times blah, 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 lots of things that goes on in physics, because a lot of what we're deciding on doesn't have that complicated physical nature. But discrete optimization modelers abuse integers in many ways, right? And so the interesting thing is we don't know if the burden of units will be seen as worthwhile by users. We think so. We believe that the more you understand, the more you get used to using them, the more type errors that are found for you before you have to do some horrible debugging, the better off you are. But we're going to need some years of user experience to really know. But we'll certainly be making unit types available in future releases of MiniZinc, and we'll see how it goes in terms of that burden. So unit types, one of the reasons they're not used is often people just find the burden of using them to be not worth the value they give. I think in discrete optimization modeling, the burden is, let's say, the same, but the value is more pronounced because debugging is so much harder. All right, that's the end of my talk. If you have any questions, I'll be online to answer them. And if you're interested in MiniZinc, you can find it at minizinc.org. Thanks very much.